Okay, let's go ahead and finish the notes here. We're down to like a couple more pages and then we'll be finished. Okay. The next topic that we're talking about is going to be centripetal force. Some people call it centripetal force. Okay. But we've already talked about that word force. So it is a little, hopefully it's a little familiar to you. Centripetal force definition is here's the word net. We used that word before. The net force, right? The word net force means the overall force of everything acting on it, required to keep an object moving in a circular, can't even speak today, path. Okay? Now, we talked about forces before, actually in the previous unit. There were different types of forces. So let's go ahead and just recall some of those forces. One of them was tension force. Remember, it was like a string, a rope, a bungee, a chain. Another force is frictional force. Another force would be maybe gravitational force. So all of those are examples of types of forces that are used for centripetal force that is used to must be there, because if it's not there, then it won't be able to keep that object moving in a circular path. Okay? Centripetal force is always acting towards the center of the circle, right? Because that's what keeps it in. It keeps that object moving in the circle because it moves towards the center of the circle. And we're going to talk about the directions in the next page. Now, it has an equation, and hopefully you all remember the equation that we used last unit, right? F equals ma. Now, we have circles that we're talking about, centripetal. So this is actually F sub c, centripetal force, equals mass times the centripetal acceleration. So F sub c stands for centripetal force. And what was the SI unit for force? We said it last unit that we don't care what type of force. If it's force, it's going to be a Newton. M stands for mass, which is always in kilograms. I do not care what equation. If it's mass, then it's going to be kilograms. And then A sub c, which is centripetal acceleration, which is meters per second square. Again, though, this can be put into the triangle, which I love. It kind of shortcuts my algebra. Come back over here to the equation, cover up the equal part. M and A are being multiplied, so they have to be at the bottom down here. What's left over is the F sub c. Now you can just cover those up and you can see how to algebraically rearrange it without having to do that algebra. Now let's do a couple of practice problems. Okay, our notes are due the day of the test. They are not going to be submitted through Blackboard anymore. You need to turn those suckers in, and they will be due actually before the test is given. If you turn it in after the test, it's going to be late. Examples. It says here, Haley is turning in his 155 kilogram car mass with a centripetal acceleration, A sub c, of 2 meters per second squared. What's Haley's centripetal force? F sub c equals ma sub c. I'm looking for the force. I don't have to rearrange this equation. I can write it out as is. Fill in the blanks. 155 multiplied by 2 equals 310 newtons. Done. Okay. Troy is spinning a ball on a string. Now the ball has a mass of 6 kilograms and has a centripetal acceleration of 6 meters per second square. What direction is the centripetal force? Well, we just said it in our notes, and we're going to talk a little bit more detail about directions in a little bit. But in our notes, it says towards the center. So it's what we call a inward, okay, direction. All right, and what is the centrifugal force on this ball? Well, F sub C equals MAC. Not having to rearrange it, we can leave it as is. So the M is the mass, which is 6. And the acceleration is also 6, so 6 times 6 equals blank newtons. Okay, not too bad. That's an easy equation. Plus, we kind of already did that last unit. Now, on this side, let's talk about direction. So we've been using this word centrifugal, and again, some people call it centripetal. But we're going to talk about this word versus centrifugal. Okay, centrifugal versus centrifugal. Now, let's go ahead and write those words down. First one is centrifugal. And the next one is centrifugal. Okay. Is there anything that you can think of that sounded like centrifugal that you may have heard in the past? I'm not sure if you ever heard of a centrifuge. A centrifuge separates things. It spins and it spins outwards and separates it. So maybe that may be something that you can tie it to. But here's a little saying that I have. You may or may not like it. It's going to be quizzed and tested. Centripetal means towards the center. It is what we call center seeking. Centrifugal moves away from the center, and we call this one center fleeing. It's trying to get away from the center. So let's go ahead and draw those arrows in. Centrifugal is inward. Now, I don't care if we're talking about centrifugal acceleration, centrifugal force, centrifugal speed, centrifugal whatever. If they use the word centrifugal with it, then it's going to be inward. If they use the word centrifugal, centrifugal force, centrifugal acceleration, centrifugal whatever, if they use the word centrifugal in it, it is going to be an outward, away from the center direction. Okay? Let's keep going. When we're going to talk about this, it might be a little bit easier to explain it in class. We will talk about it in class, whether it's face-to-face or whether it's virtual. But we will go over the notes here in class. But let's go ahead and go through the notes now. It says here, the use or at least being familiar with this word centrifugal, okay, is common, okay? We've actually felt this centrifugal sensation before, okay? It's a sensation of an outward lean or force when experiencing a circular motion, okay? It's actually a misconception. We feel like we're getting kicked out, like we're getting thrown outward, and that's a centrifugal force, but actually it's a misconception. It's not even real. Centrifugal is really not there. Centrifugal is, but centrifugal is not there. It's not trying to shoot you out away from the circle, but the feeling that it is there feels real to us. So let's go ahead and talk about a couple of examples. Here's a really good example. When you're riding in a car, it says here, you can recall the sensation of being thrown outward away from the center. For an example, whether it's a car ride or whether it's a roller coaster ride. So I'm not sure how often you've been on roller coasters, but I'm sure some of us have probably experienced it in cars, right? So whether it's a roller coaster or a car, let's just say that the roller coaster or car is traveling and is going to do a turn. It's going to do a very sharp turn, whether it's to the right or whether it's to the left. But that sharp turn is going to make you feel like you're getting kicked or moved out towards the opposite direction. So if you're sitting here in the car, whether it's a roller coaster car or whether a regular car, for an example, and you're going to be turning towards the left, so it turns quickly towards the left, you feel like you're being flung out towards the right. if you're turning towards the right, you feel like you're being flung out towards the left, and you're not. It's a sensation that you feel, but it's actually a misconception. Centrifugal forces are not there in play, but they feel like they are. Okay, so it says here the motion of an object in a circle requires that there be an inward net force. Now, this is going to be the centripetal force requirement that keeps you in or moving in a circle. It says here that there is an inward direction acceleration. Okay? Inward direction acceleration that demands an inward force. And we'll talk about this and explain it a little bit better. Without this inward force, the object would maintain a straight line motion. Tangent to the perimeter of that circle. Without this, though, okay, without this inward force that keeps you moving in the circle, or what we call the centripetal force, then there's not going to be a circle. Okay, it's impossible to keep that circle moving or that object moving in the circle if we don't have this centripetal force. It feels like it's centrifugal, like you're being kicked out, but that's really not it. It's centripetal that keeps you in. Now, the sensation of being thrown outward, right? Because you're in the car and you're traveling straight and you do a really hard turn to the left. And the moment that you turn like that, your body feels like you're being flung to the other side of the car. You're sitting here and you like hit the outside or the door on the right side of the car, right? You start to brace yourself because you know you're going to do that hard turn to the left, and you better watch out because you're going to be falling towards the right, it feels like. But that's actually Newton's law of inertia. You were actually moving in that straight line, which is tangent line. And what caused you to stay in, because this car turned like this, right? You that are sitting in here feel like you're being kicked over here, but actually you were moving towards a straight line, tangent to the circle, okay? Which is Newton's first law of motion, which is called the law of inertia. An object in motion will stay in motion. You were continually to travel this direction, but the car that you're sitting in, the door, is a force that's keeping you in the car so that way you can make that circular turn. Okay? So rather than the ideal force, there is a force pushing you outward, which is not there. It's actually Newton's first law of inertia. An object in motion is going to continue in motion in that straight line. Okay? When making that left turn in the car, your tendency will be to throwing, or that your body's thrown rightward across the seat away from the center of that circle or car. All right? And this was not due to a force. It is not due to a force. That is not centrifugal. That's what it feels like, but it's not due to that. It was due to the tendency to travel in a straight line while the car seat is making its turn. In fact, you were not thrown rightward at all. You were moving in a perfectly, an object in motion is going to stay in motion, straight line until that door caused you to turn and stay within the car so you can make a circular turn or a curve towards the left. If an airborne camera had collected the motion on film from above, we could watch, it says here, the instant replay, then it would be a no-brainer. It says here that the car would have turned left and your body would have kept going actually straight, even though it feels like a centrifugal force. It's not. Finally, your body hits the door on the right side of the car, and the door provides an inward push on your body and causes your body to begin to moving in that circular curved path. Okay, so we'll talk about this a little bit more. Again, anytime throughout the notes here, this is how we're going to do notes. We're going to continue to do notes this way, and in class we'll talk about them. That way we can cut back on time so we're not writing them down in class. But please highlight, use some of those little sticky notes so that way you can ask me in class if you have any questions. Now, this is just kind of a little summary of everything that we learned, because my goodness, we went over new equations. We got new variables, right? The omega, we already knew what a theta was. We're no longer talking about linear direction. That's in a straight line. We're talking about circular motion. Okay, so we cannot use the same equations that we've used before. So linear, if we're talking about displacement, it used to be a D. This stood for displacement or distance. For angular, moving in a circle, displacement is a theta. Remember, that theta is not in degrees. It's in what we call rads. Velocity or speed would be a V or an S. Remember, they're used interchangeable. But for angular motion, talking about an object moving a circular path, it's V sub t or it's omega. It's a weird W. Okay. Acceleration, remember A for acceleration. Here is A sub c because it's centripetal acceleration. All right. Now, let's just go ahead and look at how these equations are a little similar, but yet they're definitely different. If we're looking for distance, okay, we had two ways we can look for distance. We can use the velocity or speed equation, which is V equals d over t, or S equals d over t. Also, though, in a straight line, we got final position minus initial position, and that displacement, when we subtract them, was the distance that that object traveled. Now, talking about circular motion, though, we don't have that option. We can't find the final position and the beginning position and use a ruler for a straight line. But we can find distance by using the velocity V equals d over t, rearranging it, because this equation is the same as this equation, rearranging it to say distance equals V times t. Well, what is my circular motion equation? Theta, remember it's in rads, equals omega times time. Okay, what about if I want to find the distance? Remember, this is considered to be our distance in circular motion. What about acceleration? Final velocity minus initial velocity divided by time. That was our equation. Then we're able to use kinematics. And believe it or not, there's kinematics for circular motion. We're just not going to get into that this year. We're going to just cut that out, so that way we can move on to another topic. But there is more details, depths into this circular motion. This was a simple plain Jane equation, or you may look at it or recall it as A equals triangle V, right? The change in, which is this, over T, or sometimes it may have been triangle T. Here, it would be A sub C equals VT square over R, radius. And V, velocity, equals d over t. But remember, we actually said that there was 3 different equations. Because speed and velocity are interchangeable, we can do number 1, omega equals theta over time, which is the same as this one rearranged. Or number 2, we can use v sub t equals 2 pi r over capital T for period. Or we could use this one right here. It's not used too often, but we're more than welcome to use it. V sub t equals r times omega. Okay, all 3 of them work, depending on which variables you were given. Okay, now I know we've already talked about first semester a lot of variables, okay, or in symbols, but here are some variables over here. What do they mean and what are the units that go along with these symbols that we're looking at? So a theta sign here stands for displacement, right? And what is the SI unit that goes along with this theta is a rad, right? A rad. Okay. This is an omega sign, which stands for speed, which is rad per second. Acceleration, or let me white that out. Let me go back. Centripetal acceleration is meters per second square, or it may be rads, because rads is a distance and meters is a distance per second square. Okay, next one, lowercase t stands for time, that's in seconds. Lowercase s stands for arc length, which is distance in meters around the circumference of that circle. Lowercase r stands for radius, which is a distance, which is also meters. Lowercase f stands for frequency, which is hertz, Hz. Capital T stands for period, which is seconds. Maybe this might help us a little bit because all of these you have to memorize. V sub t stands for tangential velocity, right? So tangential velocity. And tangential velocity is going to be in meters per second. Or if we're using the other one, it could be rad per second, because rad is a distance, just like meters is. Okay. VT square, right? Which is just the square root of tangential velocity squared. I'm just going to put tangential velocity. Put square like that, right? It's just square, which in this case we end up with meters per second square or rads per second square. We get that square from it. And then F sub c is centripetal force. Which is in a Newton, okay? So our notes are finished now, okay? You need to get these notes done before you come to class. I'm telling you, from here on out, for the rest of the semester, that's what we're going to do. Do the notes at home, get them filled all the way out, have your questions, mark it, highlighted here, or on another piece of paper, and when we go through them, whether it's person to person in class or whether it's virtual on Friday, we're going to go through the notes. You need to ask me. That is our number one thing that's going to hurt us, is not asking questions, okay? I want you to be successful this year, all right? I will go back after we have our classes start and after we go through this in class. I don't want to, ruin it before we actually have class because there's a lab to go along with this. I will then go ahead and video this and post this as well, okay? Other than that, have a great day. I can't wait to see you all.